Hello everyone. Welcome to the tutorial 4 of Chords command. So I'll just wait for maybe 30 seconds to let the people join and I will start. Okay, let's start. Hi everyone, I'm Madhumita Malik from Huawei Technologies and I welcome you to the fourth tutorial session, tutorial 4 of Chords command today. And this tutorial is titled Code Mixed NLG, Resources, Metrics and Challenges. And in the tutorial, they will discuss the adaptability, limitations and challenges with various evaluation metrics for the code mixed NLG. And we are hoping for an exciting session. This session will be given by Vivek Srivastava, who is a researcher in TCS Research Pune, and Professor Mayank Singh, who is an assistant professor at IIT Gandhinagar. So over to you, Vivek and Mayank. And before we start, a small request: please post your questions on the Q&A tab, and we will take it up as we go on. Thank you so much.
Thanks, Madhumita, for the introduction. So in this tutorial, me and Professor Mike will walk you through the various available resources, matrix, and various challenges that we saw along the way with the code mix NLG task. We'll talk about different tasks, and we'll see how these things evolve and where we can take it forward from there. So this entire tutorial is divided into three different parts. In part one, we will discuss what is code mixing. We will see various real world examples and different use cases. Then we'll see how we can really measure the complexity of code mixing, or the degree of code mixing in the text. What are the different metrics available for that? What are the different challenges and limitations that we have with these metrics? In the second part, we will take this discussion forward and see one application of code mixing in various NLG tasks. We will see what are the different resources that are available. Then we'll see what are the different metrics, how the widely popular metrics which are available for monolingual NLG, how do they work with the code mixing setup, and then just a spoiler alert, they don't work well, and then we have proposed a pipeline that tries to address this problem of these metrics not performing well with code mixing. Uh, in the third part of the tutorial, we will see what are the different challenges that we saw, what is the limitation, and where is the impact in this low resource setup of code mixing. And what's next? Towards the end, we will see what are the different future direction and what are the different open research questions. So uh, just a heads up that part three was earlier planned for Professor Mang, but due to some health concern, he won't be able to deliver that. So I guess bad luck. You will have to go with me for the entire 1.5 hour. And so let's start with the part one. So code mixing, by definition, is a phenomena of mixing words and phrases from two different languages. We can have more than two different languages as well. The example that you are seeing here is taken from the Twitter handle of Paytm, which is one of the very popular brands in India. And this is in their poster they have this code mix sentence, code mix text, which has words from the Hindi as well as English language. And the idea is to reach to a certain group in the society by mixing these words and sound familiar with whatever happening with the app that people use. So this is a very good kind of advertising strategy that people use nowadays. There is one more thing, interesting thing, which is there in the bio, and this is I will come to this part whether this is a code mix sentence or not. So a part of it looks like a Hindi word, and a part of it is the name of the brand. So is it really a code mix thing or not? So I will come to that. So Paytm is not the only example. So a lot of other brands also use code mixing to convey or to engage the audience, right? And this is one interesting example where Zomato has posted some time back that there is a caption which is written in English, and there is a Hindi overlay text on the image. So this is sort of an example of multimodal code mixing, and this is an open research area. People have generally not addressed this kind of problem so far. So we have seen works where people address text independently, where they address audio independently, but multimodal kind of thing is still out of the picture. So this is an open area where people can work on. So far we have seen Hindi English as the code mix language, but that's not the only code mix language pair that we have. We have code mixing spanning across different parts of India, and not only India. We have code mixing beyond India as well. People very frequently communicate across different parts of world, such as Spain and China even. So we have seen numerous examples over the year that people very frequently use it on social media platform to engage with the similar kind of audience, and the response is also very great in that. So the question is, do you code mix? And there was this study from David Crystal around 2004, and he has projected that when the population will reach around 350 million, the number of English speakers will outrun the number of native English speakers, and this is quite big. And and if you see, this study was sometime around 2 decades back, right? And with the increasing use of social media and other internet mediums, people generally come up with these kind of languages, and they try to converse with these languages. So I believe that this number has already been achieved, and this is only for one language. This is only for English. So if you see, this is a global phenomenon, and this problem needs to be addressed. And we need to address different parts of the setup, where not only NLG tasks but also other problems could be taken. So let's see two examples here and try to see what our understanding of code mixing is so far. Because I have given you the definition, I have given you some real case use cases of how people are actually using code mixing. So, uh, uh, very sorry if you're not a Hindi speaker, uh, because I am not comfortable with any other language apart from Hindi. So I took this example. And if you can guess what is the language of this, maybe you look at the words, and what will you come up with is that this looks like a Hindi sentence, because there is no word from either English or any other language, right? But there is a catch, that Hindi is usually written in Devanagari script. But what we are seeing here on the screen is not really a Devanagari script. This is Romanized Hindi, and all the problems start coming up when you change the script of the language. And because there is no grammar, there is no syntax, there is no standard for spellings, and everything comes up. All the problems start creating up once you do this. And English is out of the picture because we don't have these languages present here. Let's see another example. This example, I think majority of you will say that this is a English text, right? Because the first two tokens looks like they are written in Hindi, Romanized Hindi, and the rest of them are the English language token. But that's not really the case. This entire Bharatiya Janata Party, the named entity that we have, is actually a code mix named entity in itself. So what will it make is that whatever language you will choose, you will write Bharatiya Janata Party as it is, right? So it's a language independent entity in itself. So it will make the entire text English. If you remember the Paytm Karo example that we had in the bio of Paytm, that was a similar example where Paytm was the named entity and the rest of the token was coming from the Hindi language. So Hindi and Romanized Hindi, they are out of the picture. So because we are not really using those languages to write the text here. And what will happen if we merge these two examples? And as I have already told you, the first one is the Hindi language, the second one is the English language text. And this is what we call it as the code mixed example, or English specifically here. Uh, we have words coming from two different languages. We can have words coming from more than two different languages as well. And this is a typical example of a English text where we have words from two different languages. But can we measure the degree of code mixing? Can we quantify how much code mix a given sentence is? On, let's say, on a scale of 0 to 100, can we say that this text is 54% code mix? Can we can we assign a number to that sentence? Fortunately, the answer to that question is yes. We have a lot of work going on. People have worked on this field for more than a decade now, and we have. So in this tutorial, we will discuss 5 different metrics. First one is the CMI, code mixing index, which is very popularly used. There are variants of these metrics which are there in the literature, but we'll stick to the fundamental ones, and we'll see how these metrics perform. So the first example is code mixing index, and it measures the degree of code mixing. If you see the formulation of CMI, it looks like that. Let me break down the different components for you. WI is the number of words in language I. Since we can have multiple languages, this WI will change given a certain language. Max WI represents the number of word in the most prominent language. By most prominent language, I means the language which has the maximum number of tokens. N is the total number of tokens is that in the text. U is the language independent tokens. One example we have already seen that named entities are language independent. If you put everything together, the score that you will get for a text is in between 0 to 100, and 0 here represents that your text is monolingual, and as you move towards the other end of the scale, it shows that the text is highly code mixed. So let's see how it works with the examples. Here I have taken 3 different examples from Shah Rukh Khan movies. The first one is monolingual, where we have all the Hindi tokens there, and the second and third examples are the code mixed examples, where we we have words in English as well as Hindi language. For the English language tokens are marked with blue color here in both the examples. Uh, if I give these examples to you and ask, like, what do you think, which one is the more code mix sentence, that probably the answer would be the third one, the third example in this table, probably because in this it looks like the English sentences are given in the English sentences has English phrases, not only just words, unlike this example in given in this table. And also they are unique. So in example 2 we have word minute repeated, but here we have unique phrases, so it looks like that third sentence might be more code mixed as compared to the second one. Let's see what CMI tells us. If you compute all these different components that we have in this matrix, what will come up as the final CMI score is this. So 0 is for the monolingual, because we know that this is the monolingual text. 28.57 and 19.04. So the matrix is saying us that the second sentence, the second example that we have, is more code mix as compared to the third one. Uh, that's not true, right? If you are going with your assumption, so we will see why this is happening, why this is the case, that what looks good to us is not coming up. Let's see another matrix. Let's see the second matrix that we have listed now, which is multilingual index, which measures the inequality of distribution of language tags. So how unequally the language tags are distributed in the text, we will see that. The formulation is again as given here. Uh, there are 2 things here. First one is PJ, which is the probability of seeing a word in a language J over the total number of words in the text. K is again the total number of languages in the text. We can have more than 2 languages here. If you compute the M index for a sentence, it will range from 0 to 1. A score closer to 0 says that you have a monolingual text. A score closer to 1 says that you have a perfectly code mixed sentence, that the distribution of language tags is uniform. Let's see with our example, the examples that we have took earlier. what does the M index says here? So if you compute these scores, again you will see that the second example that we have for code mixing is assigned a much higher score as compared to the third one. Your curiosity might be increasing here, why it is happening. So we will talk about that in a couple of minutes. This why this is happening and why it is important to look at. The third matrix that we have is integration index, and it measures the probability of switching within a text. So we can switch from one language to another language, and what is the probability of switching within that particular text. The one component to this formulation is si, I plus one. So it considers the switching that will happen for a language tag. So let's say you have a language tag of I plus one token, and you have the language tag of I token. This particular value will be one if those language tags are different, and if the language tags are similar, you will get a score of 0. So if you put everything together and compute the I index for a sentence, you will get a score from 0 to 1. And again, 0 to 1, this scale represents that uh, um, the 0 will be much closer to a monolingual text. One will be again the perfectly code mixed sentence where you have consecutive language switching between the two languages that are there. So if we go to our examples and compute the I index for those sentences, again you will see the similar pattern has emerged, that the second example is getting more score as compared to the third one. And the reason why it is happening is what we'll discuss in a couple of minutes. So one thing I wanted to talk to you about again. So this 0 1 score. So it depends on these language tags. So the first token and second token share the similar language tag. So the score assigned is 0 here. And the first token and second token share the different language tag. So the score assigned here is 1. So the next matrix that we have is burstiness, and it measures whether switching occurs in burst, or the switching that happens is having a periodic character. So uh, now we don't talk about words here in this metric. We talk about language spans, and sigma r denotes the standard deviation of the language spans, and mr denotes the mean of the language spans. And if you put everything together, the burstiness score that will come is in the range of -1 to 1. If you are getting a score closer to -1, it means that the switching is happening as a periodic nature. If you are getting a score closer to 1, it means that the switching has a bursty nature, and in between you have a neutral behavior. So if you go back to the examples again, I don't think there is a clear pattern here, but it says that since all the scores are very closer to 0 and somewhere around this scale, it means that there is some kind of periodic nature, but things are mostly neutral in all the three examples. This is the final metric that I want to talk about, and this is memory, which quantifies the extent to which the length of language spans gets influenced by the length of language spans preceding them. So what was the language span of the previous what was the length of the language span of the previous span, and how does it influence the next language span. So this is the formulation, and again sigma 1 and mu 1 is the standard deviation and mean of all language spans, but you skip the last one. Sigma 2 and mu 2 is the standard deviation and mean of all language spans, but we skip the first language span. NR is the number of language spans. Tau I is specific language span in the utterance. And when you put everything together, the score for a particular sentence will be in the range of -1 to 1. -1 represents here that a long span will be followed by a short span, or a short span will be followed by a long span. And if you go towards the other end of this scale, it means that you have equal size span for both the languages. Again, if we go back to our example, the scores will turn out to be this. And uh, so had it been the case that you had one here, one in the sense that only one token from this particular language, then the score would have been one in this case. But since that is not the case, we are getting a score closer to 0, which is on the positive side of that scale. And So the question that I have posed is that why did it look like that third sentence was more code mix, but it was getting much lower score as compared to the second sentence. So we tried to address that, and try to not really address, but we tried to explore why that was happening and why, what are the different reasons for that. And so this is the paper that we wrote some time back. And what we did here is there are 10 different data sets, and uh, which we took, which was quite popularly used across 8 different tasks at that time. And uh, if you see that majority of these papers have used CMI to report the quality of the data set. So how good the sentences are there in the data set, or how code mix the sentences are there in the data set. So this metric is very popularly used across the literature. So what we did was we proposed two different measures, on which how we can actually measure what is happening in the text. So the first one is the degree of code mixing, and it can range from 0 to 10. So a DCM score of 0, a degree of code mixing score of 0, says that the text under consideration is monolingual. And if we move towards the other end of the scale and we get a score of, let's say, 10, it says that we have a high degree of code mixing. Apart from, we don't only look at the degree of code mixing, we also look at how readable the sentence is. So it might not just be the case that the sentence is code mixed, but it should also be readable. So we again take a 0 to 10 scale, and score of 0 suggests that the text is completely unreadable by the annotator, and a score of 10 suggests that it is highly readable, and the semantics is clear, and we have easy to read words. So what we did, so we have 10 different data sets, and we picked one sentence from each of the data sets. uh, the Hindi tokens here are marked with orange color, the English tokens here are marked with blue color. And the first thing that we did was this thing. So we computed all the 5 different metric scores that we have discussed earlier, and we normalize the CMI, M index, and I index in the range of 0 to 10, such that they are in the similar range for DCM and RA. Burstiness and memory is in the range of -1 to 1. So what was the first thing that we observed? So there is a lack of consensus within the matrix itself. So if you look at these two examples, what is happening is that uh, the pattern is similar. So a chunk of Hindi text is followed by English text here, and here the chunk of English text is followed by Hindi text. But if you look at the metric scores, I don't think you will be able to pick one particular metric score that this metric is giving us a very clear idea of what is happening inside that text, and how complex or how code makes that particular text is. So there is clearly a lack of consensus within the matrix itself. Then what we did, we took 3 different annotators. We asked them to rate these sentences on these two scales, the DCM and the readability score. We gave them these 10 sentences. We asked them to do these annotation. These are the scores that we got. And the first thing is that we observed is that there is a high disagreement between humans itself. So if you pick two sentences, and you will see that these two sentences, and if you will see that the scores assigned by human 1 and the score assigned by human 2 and human 3, so these they have an entire range of scores that are being given, right? And the second thing that we saw, that uh, degree of code mixing and readability, so they doesn't go hand in hand. So it doesn't mean that if the degree of code mixing is very high, the readability will also be very high, so, and vice versa. So these two things actually impact how your scores are being calculated, and this is really not being taken care into in any of these metrics that you are seeing. And also in the next iterations of what people have worked on, they have really not uh, considered these kind of behaviors, that like, uh, should we also consider readability into consideration while assigning a score to a particular sentence. So this is still an open area of exploration that people can take up. So let's say there is a setup where you have a large scale noisy data and you want to filter a code mix data from there. There are two paths that you can take in general. And the first one is you employ the human annotators, and the second one is you employ the code mixing matrix. So you pass the sentence through a code mixing matrix, and you ask what is the score, and based on that you do a thresholding, and then you say that okay, if I'm getting a score greater than 5, the sentence will be code mix, and I will filter it out. And these code mixing matrix, they actually depends heavily on these LID systems. So by LID system, I mean language identification tools that we have, and that is where all the problem is. So we identify three different problems, and their combinations are making it very difficult to do this entire solution for this large scale noisy data to filtered code mix data problem. The first one is the matrix itself are very difficult to come up with a certain conclusion. The problem is they address everything as a bag of word model. They don't really consider context into account. And the second thing is that these LID systems, so these language identification systems, they don't really work that well on the code mix data. So even if you pick any state of the art multilingual solution for language identification, you won't get very good results. And specific to code mix, I don't think there is anything which is currently uh, that great that you can totally rely on that system to do the language identification. Misleading score, we have already seen that there is no consensus between the matrix, so you won't be able to pick one particular metric for a task. High inference time is there, so if you switch from LID system to this path of human annotation, so there is a high inference time that you will suffer here. Also, the cost is also very high, so this path is also not feasible to take. So there are a couple of examples that we try to understand under each of these categories. For metric formulation, if you see, if you pick any example from these data sets and just randomly shuffle the words, what will happen is majority of these metrics will say that the same score is being assigned. So if you look at the second sentence, it doesn't make any sense. It's just more funnier than what the situation is. Uh, the second sentence again, if you just randomly shuffle the majority of the matrix, they say that the score is same for both the sentences, and this is happening because you have a bag of word setup. This was actually what was impacting the examples that we saw, that movie dialogues that we were having, because we only consider bag of words. The third example that we had, it had more number of tokens, and because of that the score was coming down for most of the metrics. If you look at multilingual language identification solution, we tried to pick a couple of them, and we ran it for this one particular example. If you see that wherever the human has given the English label to the particular token, these metrics are also saying that this is English. But for others, there is a high disagreement. For the tokens where, let's say, this is Hindi, the other metrics are quite confused what this particular token is. So this is not something state of the art for code mixing, so to say. And again, it is very evident that human annotation is very difficult. So I will talk in detail about what we can do, or this entire area of exploration for human annotation or human evaluation for code mixing, because we need to come up with policies that can actually help the annotator to do the correct sort of annotation for these tasks. So the question is still there, that are we sure that you code mix? Because uh, there are metrics, there are things that can measure that, but with the current metric formulation and the available resources and the difficulty for human annotators, I don't think that we will be surely and confidently be able to comment that yes, we can say that the text is code mixed or not. So this is the end of the first part, and we have seen code mixing. How do we measure the complexity of the text, and challenges and limitations? So yeah.
So Vivek, I think there are a few questions. First comes from Sumant Kulkarni. He's asking, can CMI help if we have more than two languages in focus?
Uh, I because even having two languages is very difficult. So if you see that with two languages, it's not working well. So if you have more languages, it's going to be very difficult. The problem here is that the language identification tool, the dependency on the language identification tool that we have. So uh, it won't work. It won't work that great, but you will get some score at least.
Okay, and he's asking another question. He's saying, "Oh, Mayank, did you have anything to add?" I'm sorry. Oh, okay.
Yes.
So,
So actually,
yeah.
I had sent the same answer to Sumant for this question. So
Okay, okay.
yeah. So CMI is defined for multiple languages, but again, it is not going to help us if you have increase the number of languages.
Okay, so another question is from Suman. How did you separate Hindi and English tokens in datasets? Slide 36 and 37, I think it had the reference.
Okay. Uh, okay. So the 10 examples that we have picked, right? If I'm correct.
Yes.
So we did that manually. We did on our own. We didn't use any language identification tool there, and that was the reason we couldn't scale beyond 10 sentences, because that's very difficult for even for us to do the annotation.
Okay, and okay, there are a few questions. Okay, one is why is bow a problem? Yeah, bag of
Uh,
words.
that is a good question. So I think I have covered it here somewhere here. So if you look at this example, if you just shuffle these words, the CMI score will remain same, or all these matrix score will remain same, even though the sentence doesn't make any sense. If you read the sentence, it doesn't make any sense, but the CMI score is similar, right? So this is one of the very biggest reason that these matrix where they fail. Yeah.
Okay, and I think we'll take. Okay, there are two questions actually. One is how about code mix with different scripts like English with Devanagari script for Hindi? Yeah,
Uh, what do we want to do? Do we want to compute CMI and all these scores?
yeah. I think that's the
Again,
question.
that will be problematic, right? It's
Right,
not only about language identification. It's about bag of word model. It's about how the metric is formulated itself. So those things will still remain there even if you change the language. Um, but I don't think it will perform perfectly. There will be edge cases where it will fail, and there will be cases where it won't give you the correct idea of what the score is and what the sentence is.
okay, thanks, Vivek. One more question from Rachit. He's asking how is the readability measured for the sentences?
How is, sorry?
How is the readability measured for the sentences?
So that is qualitative sort of. So that depends on how the annotator uh, sees the sentence, how easy it is for the annotator to read the sentence. So because we had three different annotators, and you can see that there was a range of scores that was assigned to the sentence. So it depends on different annotators as well.
Right. Okay, thank you so much. Thanks. Okay, I think we have questions coming. Okay, one is where can you apply code mixing? Is it part of pre-processing or tokenization?
Uh, the application of code mixing is in various domains. Let's say you pick a very simple task of searching a particular item, uh, maybe for recommendation, maybe for retrieval of documents, uh, maybe for retrieval of tweets if you want to do that. If all the systems are built across only monolingual language, you won't be able to get good results in that. Maybe in search recommendation and filtering, all these things, we have applications across different tasks. We will see one example, one application area of NLG in this tutorial. Just it's coming after this, so we'll discuss that.
Yeah, sure, Vivek. So I will say, go ahead, Mayank. The questions, it will be great. Maybe you can just answer in the same tab. Then everyone will also have the answer to the questions. The people are asking essentially. Yeah.
Sure, Madhumita,
So
but somehow it is
yeah.
actually not allowing me to answer.
Oh, okay.
Yeah,
No worries. Sure, sure.
yeah.
So we'll go ahead and Vivek, please go ahead. The
Sure.
next part. Yeah.
So in the second part of the tutorial is we'll talk about one of the applications. There were a couple of good questions on how we will apply this code mixing and whatever we are seeing right now in the real world scenario. So this is one particular domain of natural language generation. What happens in a typical NLG system is you give an input, and the text as an output is expected out of the system. The input can be anything. It can be a text or a non-textual document as well, and the text as an output remains same. But for us it is code mix NLG, right? So we are talking about that, and which side of this setup the code mix text will come. So there is no fixed rule. So we can have a code mix text as an input, we can have a code mix text as an output, and we will see 5 different data sets here. And we will see that it's not really important that which side of the whole setup that code mix text is there, but it's going to be problematic until and unless you don't have the code mix text. So the first data set, it is one of the very first works across this whole natural language generation setup. They have proposed a goal-oriented code mix conversation, and this data set is actually uh, taken. Let's say the source for this data set is a second dialog state tracking challenge, which we call as DSTC2, which was proposed around somewhere around 2014, and this dataset was adapted in 2017 by Bordis and Weston. And what happens here is there is a user and a bot, and user tries to do the reservation in a particular restaurant. He will set up a certain constraint to the bot. They will ask different questions, and the bot will respond accordingly, suggest different options, and then do the reservation. So this entire data set that we have here, it is in the English language. And what they did was they tried to create the code mix version of this data set. uh, this is the distribution of the data set. So we have around 50,000 number of utterances. The unique utterances is around 7,000, and to create this code mix dataset, they have created this dataset in 4 different languages: Hindi English, Bengali English, Gujarati English, and Tamil English. So what they did was they picked a mix of in-house and crowdsource annotators, because not everything was available in-house. So this is the distribution of the in-house workers. It looks like that majority of them are the male annotators. Their highest qualification is uniformly distributed across all the 3 categories, and they frequently use both the language, the native language as well as English, to speak, write, and do the communication. And if we come to these 4 data sets that they have generated, the number here represents that the 0% of in-house annotators were used and the 100% of crowdsourced annotators were used. This pattern is similar for all the other 3 datasets as well. This is a distribution of what we have in the Hindi, Bengali, Gujarati, and Tamil datasets. If you look at these numbers, that we have pure native language utterances as well. Why it is happening is, uh, if you go back to this particular example, there are sentences which only has one word, which is there either in English or in that particular language, right? So this number comes up here, that we have pure native language utterance, we have pure English utterance as well, and that's how they have created the data set. And they do the quality evaluation. So what they do is they take 3 in-house evaluators for each of these 4 languages, and there are three various dimensions across which they measure. The rating scale is 1 to 5 for each of the annotators, and they ask them to annotate each sentences, like what different score they will assign. The average is given here, and if you see that these average scores are very closer to 4 or even 5 in some cases, and it means that the sentences which are being generated, they are easy to read, and the coherency is very great. So the dataset looks good. The dataset looks good enough to use across the uh, different languages in the Indian setup. And this is one, and I think the only dataset which is there for the goal-oriented code mix conversation. The second data set that we have is for machine translation, where and this is very specific to the English language that we have been talking about. And what they do is, so this dataset came around 2018, and at that time they picked these three already available resources which were there in the literature, and they had different tasks as their original setup. If you merge everything, the number of English sentences that we will have is roughly around 6,000, and they have employed four different annotators to do the English translation, so English to English translation of the sentences, and the evaluation, because it is very difficult to uh, translate one sentence by two different annotators or even more than that. So what they did was they randomly sampled 100 sentences, and whatever is being generated by one annotator, they asked the other three annotators to just uh, do a binary classification whether the sentence is correctly generated or it needs correction. So based on that, the Fleece Kappa score is calculated, and it's around 0.88. The maximum it can take is 1. So that means the score that we are having is suggests that the translation done by the annotators is very good, and this is the final data set that we get. So we can take English and English on both the sites and do this machine translation setup. The third data set that I want to talk about is the Fink dataset proposed by us sometime to 2020, 2 years later from this second dataset. But why a new dataset? Because we already had one dataset, and it looks good. It looks good that the sentences were generated by the human annotators, and we had a very good dataset. But there are problems with that dataset, and the first thing is there is a lot of spelling variations which are there in the English sentences as well as the English sentences which were there in the dataset. The short sentences is a problem. So roughly around 12% of the sentences has less than or equal to 3 tokens, and that means you don't have a very uh, flexibility in terms of doing the code mixing, because it's just 3 tokens, right? So that is one of the very biggest challenge, and we saw that sentences were ambiguous as well. We have given these examples in our paper. There were sentences where the abusive words were there, and the sentences were also abusive, so we tried to not include those kind of sentences in our setup. We saw that in the English side of the data set, there were sentences which were completely English and they were really not code mixed. So this is one of the very biggest challenge that we saw, that because this is a translation task, and if you don't even have the English sentence on the English side, so it's just an English to English translation, right? So it doesn't satisfy the whole idea of doing the machine translation. So what we did was, we instead of taking 3 different data sets, we took a much larger set of different data sets. In contrast to 6,000 English sentences, we got 52,000 English sentences. We could have also done the similar thing, that you just pick the English sentence, ask the annotators to do the annotation and translate all the sentences into English. But again, the problem will still be there. So there will be sentences which are short and they doesn't convey much of the code mixing. So we removed those short and long sentences. Long sentences were removed because it's very difficult for the annotators to translate. So we removed those sentences. The second thing that we did was, we identified the sentences where the out of vocabulary words which are there, if they belong in this range of 50 to 90% of all the tokens. So we remove those sentences, because it might happen that these sentences will be monolingual, because the dictionary which is there to identify the out of vocabulary words, it doesn't identify, it identifies most of the words as not belonging to that dictionary, right? The third thing that we did was, we removed the abusive sentences based on a dictionary, and then and then we completely discarded those sentences from the dataset. As after this pre-processing step, we got roughly around 25,000 English sentences. We took 54 annotators, and they had 400 sentences each. We have given them 400 sentences each to do the annotation. Towards the end of this, we got roughly around 14,000 English to English parallel sentence pairs. So we can use English and English on either side of that setup. The fourth data set. So whatever sorry. So whatever we have seen so far, the R4 data set that we have. In all the first three data sets, we had in sentences generated by annotators. There was no uh, uh, synthetic or even the NLG systems in place that can generate these code mix sentences, right? But this is one of the very earliest steps towards generating the synthetic code mix sentences. The first step still remains the human or the algorithmic generated step, where what they have is they have English sentence and 8 different languages. So these are 8 different parallel data sets that they have. uh, this is one of the examples how they did. So first, they use the matrix language frame theory, where uh, these languages are treated as matrix language, which means that the grammar or or the structure of the sentence will be formed from these language. The words from the English language will be embedded into this sentence. So this is how the final English in the sentence looks like. The grammar is for the is set up by the Hindi language, and the words from the English language are just added here or embedded here. So the alignment matrix. So one constraint that they have is they only pick named entity, noun phrases, and POS tags. For POS tags, they only consider adjectives. So even though you get all these alignments between tokens, you don't pick everything to do the replacement. You only pick named entities, noun phrases, and adjective POS tags. So all the blue alignments that you are seeing, so only these will be used to do the replacement here in the final text. So once you get this alignment, like girl and ladki, you replace the word ladki with the English word girl, right? So this is how they finally generate the English Hindi data set. And this was done automatically. It was not we didn't had any human annotator in place to generate this data set. And that allows us to create very large data sets as well at the same time. So if you look at all these language pairs, you will see that a large number of sentences were being generated, and all these code mix sentences that you're seeing will be used to actually create a code mixed NLG generator, right, later on. So they divide the entire sentences into train, development, and test, and then we'll look at this. So this is how the entire setup is. So the task here is you pick an English sentence and you generate the corresponding English, Hindi, or whatever it is. So there are 8 different languages, right? So we can generate sentences in 8 different languages. They use an encoder decoder architecture, where the input to the encoder is you encode the English sentence along with the linguistic features such as named entities and POS. The second thing that goes into encoder is the pre-trained language model feature. So they use the XLM as the language model here, and they use this pre-trained language model to get the embedding for the English sentence, and that goes into the encoder. At the decoder side, we have one layer LSTM with attention. The idea is either you copy a word at a particular timestamp from this English sentence, or you copy the word from the vocabulary. So this is the whole setup. To do the initialization of this network, they very intelligently did this parameter initialization. So what they did was, let's say instead of English and English setup, you have English and Hindi setup, where you already have this data set, English Hindi parallel data set, and you train this network and you'd get the parameters from that network and do the initialization here. So all the weights will not be randomly initialized, but they will be initialized from the network that you have trained for English Hindi. So that really helped. If you look at the paper, the results that they got, this network initialization did help in generating good quality English sentences. So this is one interesting idea where we can see that not only uh, human annotators, but also machine can also generate these sentences. And how good they will generate is what we try to see in this fifth data set, where there are two different things are at the center of attention for us. One is generation and one is evaluation. For generation, the first major question for us was how will we actually uh, get a code mix language generator, because we didn't had any of these generator at that time. So this R4 and R5, both the papers came almost at the same time, so we didn't had access to R4 at that time. So the idea was that we can use the parallel source sentences and write some algorithm so that it can generate the code mix sentence from the parallel source sentences. For evaluation, the most difficult part was that how will you get the reference human code mix sentence? Let's say you have the code mix language generator at place, but how will you actually evaluate it against the reference code mix sentences? And even if, let's say, you do the evaluation, how well it will correlate with human scores? So the correlation is again a very difficult thing to address right now. I will come to that later on. So we created this data set into three different phases. In phase one, what we did was we took IIT Bombay English in the parallel corpus. So just to clarify, this data set is only for English language, and this is one of the limitations that we have. We can't generate data into multiple other languages, because we had a lot of annotators in place for this data set. So from this data set, we took 5,000 parallel sentence pairs. We gave it to 5 different annotators. We asked them to generate English sentences in Roman script, and we asked them to not include additional words apart from what we already have in the parallel sentences. And if the pair is not a very good translation of each other, we ask them to not do the annotation for that, or not give the corresponding English sentences for that. As a result of this entire process, what we got was a 1978 parallel sentence pair with at least 2 human-generated code mix sentences. So there is no upper limit from our side. On an average, they have generated 2.5 sentences. The second phase of this algorithm, this entire process, is we give the 1978 parallel English in the sentence pair. So whatever we have got in the previous step, we take the English in the sentence pair from that, and we wrote 2 different algorithms. One is you do the simple word alignment between the English and the sentence. There are some constraints like noun and adjectives will only be considered. Then you replace words like we have seen in R4, and then we use Hindi as the matrix language. We do the romanization, and the corresponding English sentences are added to the dataset. The second algorithm differs from the first one in only the phrase alignment as compared to the word alignment, and we replace phrases in the English language with the phrase in the Hindi language and do the romanization. So these are the 2 algorithms, WAC and PAC, that we wrote at that time. The second part of this entire algorithm, this entire data set setup is the evaluation part. So we have WAC generated sentence, we have PAC generated sentence, we also have parallel English in the sentence pair, and we want to get a rating somehow for the sentences that we have generated. So we employed 8 different annotators here. We asked them to keep in mind these 3 things. So what is the similarity of the generated sentence with the parallel source sentence pairs? What is the readability, how good the readable or how readable the sentences are that we have generated, and what is the grammatical correctness of these sentences? So these 3 things that they need to keep in mind. So these are again the qualitative things that they have to consider while doing this quality evaluation of the sentences. Again, the rating scale is 1 to 10. So 1 represents the poor quality sentence being generated, and 10 represents the high quality sentence being generated. So this is the whole example of what we got towards the end of this process. We have English in the parallel sentence pair. We have human generated sentence, which can be more than 2 and at least 2. And we have 2 different sentences generated by 2 different algorithms, and corresponding to these sentences, we have rating scores being assigned by 2 different annotators. So this is how this data set looks like. This is a summary of what we have with all the 5 data sets. And if you look at this table, only in R5 we have tried to address this human rating of the sentences that we are generating. So uh, uh, the evaluation part was missing earlier to this, and people have really not tried to look into the evaluation part until this data set that we have proposed recently. So this is a very big problem, that how do we measure the code mixed NLG performance? And because once the code mixing comes into the picture, you have added complexity, because the spelling variation is there. Writing style of humans is different. We don't have any rules for syntax. There is no grammar, and so all in all, it looks like this is a Schrodinger's cat situation, that text is correct and incorrect simultaneously. So you can't really pinpoint that this is how it is, how it should be, and it is wrong at this place. So, uh, but we didn't stop at that. We wrote this paper where recently, where we proposed a metric independent pipeline for the evaluation, and we use the Hinge dataset as our evaluation, uh, uh, for the evaluation setup. What we have here is what we have seen. So we have English in the pair, we have human generated sentence, and two algorithmic generated sentence. And in this entire setup, what we will do is we will consider these two algorithms, WAC and PAC, as as the source of generating the sentence, or as the code mix NLG generator. And these reference sentences will be used to, human generated sentence will be used to do the mapping with this, or the evaluation with this. So if you have any questions so far, you can go ahead, and I will discuss in detail about how we do it.
So Vivek, I think there was one question, but Mayank has already answered. So maybe you can go ahead and
Sure, yeah, that's great.
yeah.
uh, okay, so so this is the distribution of how the ratings look like, and the ratings that we got from Annotator. So we did the averaging of the two ratings that we got. And one good thing about this is that we have the ratings across the entire scale, and not just something in the range of 6 to 10. So it might be pointed that the algorithm that we are using, they are not very fancy, and we are not using any neural network and these kind of things. But that was not the idea. The idea was to get the sentences which are incorrect as well, which are poorly generated, and we needed to study this whole phenomena across the entire scale. So we divided this entire 2 to 10 rating that we have, and we divided it into 3 different buckets. In bucket 1, we have the entire 2 to 10 ratings, sentences in 2 to 10 rating. In bucket 2, we have sentences in 2 to 5 rating, and bucket 3, we have sentences from 6 to 10 ratings. And what sorry, what we saw was that there are 4 different problems that were happening. First one is the spelling variation problem, the spelling variation of how a particular word can be written in different forms. The second thing is the language switching, which means that a particular word can be written in 2 different languages, right? Either in English or in Hindi. And there are words which are missing while generating the sentence, and we can't read every word equally. So there should be a penalty based on how important the word it is which is missing. And the fourth problem is something about the limited reference sentence. So even though we have at least 2 reference sentence for us, and on an average 2.5 reference sentence, but we don't really have a much larger scale of sentences that can do a very good evaluation. So if there are non-Hindi speakers, I will use one example, and this is the context for that there is a person A and person B and they are not having conversation. So uh, this is the context for that example that I'm giving. Let's say there is a generated sentence from the algorithm, either from WAC or PAC, and this is the sentence which is being generated. There is a reference sentence as well, and if you look uh, at what how we can do the evaluation, and the usual metric based evaluation, what they do is they will just match it directly. So what different words are matching, they will do a direct matching of those words, and then the score will be assigned that how much correctly you have generated this sentence. But that's not really correct. There are words which are there in the generated sentence and reference sentence which we could match, even though not directly. For example, these two words, and what is happening here is that there is a spelling variation between these two words. There are characters which are either being dropped or either being added, such that even though that words we might say the word similarly, but it is not written similarly, right? So can we identify it? And this was the one of the first questions that we tried to address. So what is happening here is there are three things that can happen. So either a character is being repeated. So for example, the word jaldi, where I is repeated multiple times, either to show some kind of emotion or something else, but the character is repeated. In the second case, there is a replacement with similar sounding character. So these two examples, if you look, the word C is replaced with CO is replaced with KA, and the word C is again replaced with K. Even though the spelling is different, the word will be pronounced similarly, right? The third case is the vowel omission. What happens is we have seen this. So the character A is being dropped, and even though the words are similar, the spelling is different. So what exactly is happening here? So either a character is deleted or added or replaced, and this is a very well-known problem in computer science. So we try to look it at from the edit distance perspective. The only catch here is that these words, what we try to address, is based on the sound of the character and not really just on the spelling. So how a particular word or a character is sounded. Based on that, we compute the phonetic dissimilarity between how similar these two words are, and it is based on the number of edit operations it will take to change the candidate word to the reference word, right? And the idea here is lower the PDS score or the phonetic dissimilarity score that we are getting, higher the chance of observing a spelling variation. So if the number of edit distance or the edit operations that we can take is very low, there is a high chance that the spelling variation has occurred. So it might happen that you have just dropped a character from a word and created a new spelling of that particular word, right? So yeah, this is the first thing that we did. The second thing, if you look at the generated and reference sentence, what happens is you might say that there is nothing matches in the generated and reference sentence. Why it is happening is uh, because there are words which are written in two different languages. For example, the word bath and talk, they are written in two different languages, even though they mean the same thing. And there are three different such instances in these two examples that we have. And can we identify this? Can we identify it? But there are a lot of problems that could be there while you want to identify this language switching. So what we did was we took the ID parallel corpus, as it was the most large data set available at that time for English and Hindi. We took out the English and Hindi words. From there we got the fastest 300 dimensional vectors for these words. But in our case, the words will be romanized, right? So we use the same romanization algorithm that we were using to do the romanization of the Hindi word, and we assigned the 300 dimensional vector that we got for Hindi word to the corresponding romanized word. After this step, you have the 300 dimensional vector for English, you have the 300 dimensional for Hindi. What we did was we created a bilingual shared embedding space, and we used a tool called VecMap, which brings the embedding into this same space, because the embedding space was different for English and Hindi. So once you create this shared embedding space, what you can do is, let's say there are two words, word one and word two, and there is a shared embedding space that we have already created. And the question is, how will you identify whether these two words are similar or not? Because that's the only question that you have. So whether the word is being switched into two different languages or not. So we did a very simple thing, that you compute the cosine similarity and put a threshold of zero point 0.5. This is based on empirical observation. We saw it that this was giving us words which are not very noisier, and the pairs are very not noisier. So based on that, we picked this threshold of zero point 0.5, and that's it. That's how we did this cosine similarity based thing to identify whether a language switching was happening or not. The third thing here is, let's say you have two different generated sentence, and reference sentence remains same. In the first sentence, what is happening is the word nahi, which is missing because of the spelling variation that we are seeing. And in the second case, what is happening is the word because is missing, because there is the corresponding word to that which is available, but it was there in some other language. And if you look at the generated sentence, you will realize that the word nahi, which is missing here, the importance of that word is much larger than the word uh, because, which is missing. And we should not treat both of them equally when we try to do the penalty for missing words. So these are the two things that we have. So we consider spelling variation and language switching, and we do the uh, uh, we add the penalty for that based on the how important that particular word is. So what we did was, we collected parallel English sentences from different sources. These are coming from various data sets that are available. We did the Hindi translation using Google Translate, and generated the English sentences using the algorithm that we already have, that WAC algorithm that we have. And we compute the IDF score of each word. So if the IDF score is high, and that means that the word is rare, and it should be an important word that shouldn't have been missed from the example. And sorry, I just crashed. Can you see my screen?
No, I think it is not showing at this moment.
Okay, let me share it again. Can you see it now?
Yes, it's visible again. Yeah.
Okay. Yeah. So to identify or to give the penalty for the generated sentence, what we do is we compute the sum of the IDF scores of all the missing words that are there in the generated sentence, and we normalize it by the sum of the IDF score of all the words that are there in the sentence. So that will give us the penalty for the generated sentence that we have. One last thing that we try to address is the problem of limited reference sentence. If you look at the generated and reference sentence, you will realize that there is no match actually. And if we change the reference sentence, what will happen is there are more number of things that will match now. It's just the paraphrasing of the reference that we did here. And the reference 2 is paraphrase version of reference 1. Reference 3, again, if you took and do the paraphrasing of reference 1, what will happen is there are more number of things that matches now. So what we are doing here is just we are doing the paraphrasing of references, and it's highly likely that it will give much clear idea of how we should do the evaluation and what should be the evaluation score looks like. But the problem is we don't have access to this unlimited reference sentence. In addition, we don't have access to the paraphrasing systems that can do the paraphrasing of the code mix sentences. So instead, what we did was we tried to come up with a score uh, that should have been added such that the actual score would look similar to the score which we had if we had multiple reference sentences. So what we did here is we divided the generated and reference sentence into different trigram phrases. You can see that the first trigram phrase is this one, the second trigram phrase is this one, and there's one very simple idea that you can reorder these trigram phrases such that they will generate the paraphrases of the original sentence. And what we do here is we first compute the phrase score, the score which should be assigned to each of these trigram phrases, and it's just the sum of the IDF score of words which are there in the generated and reference phrases, and the difference of the words which are missing from the generated sentence. Now we normalize it for the entire sentence. We just divide it by the number of trigram phrases in the generated sentence, and the final paraphrasing score is computed something like this. We are dividing it by the sum of the missing word penalty. Why we are doing this? Because there is a lot of missing word penalty that we have already subtracted from the phrase score, and we are addressing the missing word penalty separately as well. So we divided it by that. We added a small number such that this division doesn't go undefined. And what happens towards the end is this entire pipeline looks like this. So you have a candidate sentence which is generated by an NLG algorithm or a system. You have a reference sentence from humans. You compute a metric score and you say that score doesn't look very well. So what you will do is you will just update the metric score based on the missing word penalty which is coming, and the paraphrasing score that you have computed. And the two things that we have talked about, the spelling variation, language switching, so they will be uh, indirectly addressed in both of these systems, the spelling variation as well as the language switching. So this is how this entire pipeline looks like. So I have initially talked about the correlation between the human scores and the metric scores, and uh, this is how it looks like. So we have bucket 1, bucket 2, and bucket 3. We have two different algorithms, rack and pack, and the bold mark tokens that you're seeing here, they show that the correlation has improved. Once you apply this pipeline, the correlation will improve from here to here. So for bucket 1, bucket 3 actually, where we have good quality sentences which are from 6 to 10, we saw that for majority of them we were able to improve the human correlation between the metric score and the score which is being assigned by the annotators. For bucket 2, the problem was that the sentences were poor quality, so it is still very difficult for the annotators to do this annotation, and it's highly ambiguous as well. So maybe this could be one of the reasons why we didn't perform that well on bucket 2, and which will actually eventually impact this bucket 1 scores, right? So this was our observation in a part of the data set. We were able to improve the human correlation. So this is the end of the second part, where we saw that we have different NLG resources, and uh, we also saw that the matrix on these NLG resources doesn't perform that well, and there could be a number of things that we can do to make the metric scores look more similar to what the scores has been assigned by the human annotators. In the third part of the tutorial, what I will discuss about is what are the lessons that we learned, and what are the different current challenges, how the future would look like, and what are the different open research problems. So uh, the various lessons that we learned is that there is uh, a very high scale and availability of good quality data sets, and this is one area where I think people can really work upon if we want to see that there are systems that can address the problems of code mixing. So we need high quality data sets at very large scale. we need metrics which are very specifically dedicated for code mixing, and not something very where you directly pick something which is very widely popularly used in monolingual setup, because we have different constraints with the code mixing languages, right? So these metrics will not perform that great in this scenario. Again, the problem is there with how the sentences are being written, the grammatical standardization, uh, and because of that, we need high scale pre-processing or pre-trained tools even to do even basic tasks such as pause tagging or language identification, which is still missing from the literature. There are works around that. There are people who have tried to address that problem, but still there are things that needs to be taken care of. Uh, so one very big problem is that the generalization is not there. So uh, um, whatever is being studied is either for one language or maybe for a couple of languages in a certain geography, but we need to understand how well it will generalize when we will take other code mixing pairs as well. And there are four different dimensions where for which I want to talk about for task, resources, and experiments and matrix. First, let's see uh, how the task could how the different tasks could look like. Let's say there is this task of long sequence code mixed narratives that we can generate, and the input is very minimal. It's not the entire parallel sentence that we have, but let's say we only have a couple of keywords, and from there we want to generate a long sequence narratives. This is quite possible with the monolingual setup, where you can generate a story from just few keywords and generate a story in English language, let's say. But how about generating a story in a code mix language, and how grammatically correct that will be, and how much readable it will be? These are still an open area of exploration. Another thing is, one we already saw this, that there is definitely a need to paraphrase the code mix sentences. So let's say there is a system which takes the sentence as an input, and it can generate various paraphrases of this sentence. By paraphrasing, I don't mean that you just pick this particular word, reward, let's say, and you translate it into Hindi, but the sentences should also be unique. The sentences that we are generating, they should be unique, and they should also be correct at the same time. This is another application that we can pick up. Let's say you have a tabular data. You have a tabular data, and you want to summarize the information which is given in that tabular data into, let's say, any code mix language that you pick. Here, the example given is in English, but we can take any code mix language, and we try to summarize what is given in the tabular data, and what different important information is there that we can capture, and how well we can generate the sentences. So there are a lot of scope into this area of summarizing the tabular data into the code mix languages. One example could be, let's say you pick a cricket scorecard and you try to summarize it in a fashion that commentators do that while doing the real time commentary. So can we do the summarization in that fashion? And maybe a weather report summarization, such as what the news anchors and other people, how they summarize the weather report given a data in a code mix language. Can we do these kind of things? The other task is, let's say for a given topic you have a number of tweets which are in the monolingual language. Let's say there are two tweets for the same topic here, and can we summarize these tweets in a code mix language? We pick the information from multiple sources and we summarize that into just one sentence or a couple of sentences, and that should be a code mix sentence. And how well we can do that, and what different metrics that can be used to do the evaluation, is still an open area of exploration here. For resources, the first thing that we have already seen, that how well we can do the annotation, and what should be the practice that we need to keep in mind, such that there is a high annotator agreement for a task. And it's very difficult to find the annotators that share the similar expertise as you go into this code mixing setup. There is a very difficult. It's very difficult to find the annotators who are expert actually, and they understand both the language and not just of one particular language they are expert in, but also both the languages they should have expertise in. And what are the different annotation policies and what are the different pitfalls that we can see just at the beginning of the annotation task, and this should be clearly laid out. And uh, what different set of good and bad examples that we can give just before the annotation, such that the task gets clear to the annotators as well, because they are not they might not be the expert in the NLP task, they might not be the expert in the speech task that we want to do with the code mixing setup, but they just understand code mixing well. And how we can bridge this gap between understanding the language and understanding the task. So yeah, identifying the expert annotator is again a very difficult task. We can find the annotators who have expertise maybe in a language, maybe in both the languages, but they might not be an expert in the downstream task that we want to do. So this is again a problem right now at the moment. And how do we actually balance the linguistic diversity and syntactic variation? So uh, in the human annotation, what happens is that many a times this same sentence or the same word is written with different spelling and language switching and different forms, right? And it makes it difficult for the annotators to do the annotation. And let's say a same example is given to two different annotators, but there is a bit of syntactic variation that we make. So how well they will understand, how well they will take the same sentence and do the annotation. This is again a problem to look into. So in terms of experiments, what we can look into is there are existing multilingual resources, and how we can really use that, because let's say there is a multilingual BERT out there, and can we use it for the code mixing task? For people have tried to look into it. For a couple of tasks it works well, for a couple of tasks it doesn't work well. So what we can do, can we train, let's say, a language model on a code mix data? But again, that is a problem because we don't have large scale data sets, we don't have large scale code mixing data sets. If you have observed that list of data sets that I have shown you earlier, the 10 data set list, most of the data sets have sentences in the range of 3000 or 4000. Even if you combine all these data sets, the size will be very less, right? So training something specifically for code mixing is again a very challenging thing. Maybe we can first address the data scarcity problem, maybe by creating models that can generate the algorithm and minimizing the humans in the loop, and that will further on help in generating these kind of models. One interesting thing that we have seen in R4 was that there was an intelligent parameter initialization from English Hindi parallel machine translation setup to the English machine translation setup. So can we use the knowledge which is being learned for the monolingual task to transfer to the code mix languages? And people have tried to do this, and there are interesting results which are there in the literature. But how well and what we can progress further in this direction is still what needs to be addressed. So for metrics, I have talked about a lot. So what we can do, can we come up with metrics which are very uh, specific to the code mix languages? Can it automatically understand and address the syntactic variations or the linguistic diversity that we are talking about? uh, uh, can we have a high similarity or even uh, 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 correct similarity score or correct evaluation score based on the context, based on the spelling variations, and so on? There are so many challenges that these metrics needs to address right now for the code mix NLGs. So this is again, like, we have popular matrix blue rouge. We saw that they don't perform well for code mix NLGs, and there are several reasons for that. Spelling variation is there, switching point is there. So uh, people have tried to propose matrix which are again bag of words based, but we don't really adapt the modern embedding based evaluation matrix like bird score, and so on, for the code mixing setup. So we need to really see where it can go, and how we can leverage the modern architectures to address the problem of code mixing. And the context is what we haven't talked about a lot. So for example, if you see, the word can be written in multiple forms. The word nahi can be written in multiple ways, and if the matrix doesn't take this word into account, the problem is there, right? You will understand the sentence incorrectly, and that will result into a poor uh, evaluation score, right? For example, if you look at these two sentences, what happens here is, the word stri, which is there, it's a homonym, and it means two different things in these two sentences. And what will happen is, the matrix scores, or the widely popular matrix that we have, they will assign a very high similarity score, or the evaluation score for these two pair of sentences, but they are really different from each other, right? And it shouldn't happen that way. So I think we have covered a lot of things here in this tutorial. And initially we picked up with code mixing. We saw different matrix. We saw what we can do with these matrix, and what are the different NLG resources that we have. What are the different matrix that we have? Can we make them more correlated with the human scores? We saw what are the different future directions and open research questions. So with this, I will put an end to this tutorial, and uh, we are open to questions, feedback, and comments. These are our contact details if you want to further contact us for any doubts that you have, or anything you want to discuss specifically. Feel free to reach out, and thank you.
Vivek, so there is one question by Rachit. I have answered it for energy systems in general, but would you like to answer this in terms of pack and whack? So the question says, as I understand, there could be multiple candidate sentences with spell corrections and language switching. How is the ideal candidate sentence decided? Are the candidate sentences generated iteratively to check with each reference sentence?
So, uh, if I understood correctly, it means that we have multiple reference sentence, and how which sentence will we pick, right? So
No, no. So
we
this is something that I understood, that our whack and pack can these algorithms generate multiple sentences, and which sentence we pick?
I don't know. So our algorithm will generate only one sentence. It won't generate
Hmm.
multiple sentences.
Right,
So,
right,
so
right. So that was the
given
doubt. That's
algorithm
what.
will generate only one sentence, you have multiple reference sentence to it. So you compute the scores and take the average. That's one idea that you can take. Maybe there are ways that you can look into.
Hmm. Right. So in our case, at least it generates one sentence, but in future, new NLG algorithms might come and they might generate multiple sentences, right? So it is up to the NLG system to find out or to come up with the best candidate sentence.
Yeah, sure.
Hi, am I audible, Vivek?
Yes. Yeah.
Yeah, okay. So I think there was some network problem from my side. Anyway, so thank you so much, Mayank. You were very active on the Q&A. Vivek, if you go into the Q&A, you'll see there's at least, 15, 20 questions from all the
Okay.
audiences. And Mayank has been answered all of them. So I guess we don't have any questions at this moment. But before we end, I think there is a sponsored video. So can maybe Deepak or someone will play the video. So please stay back for the video and then we will end the session. Yeah.
Okay.
name is Tridib Mukherjee. I lead the AI and data science team at Games 24/7, which is heavily driven by the technology and data science and ML for all of its products. And today I'm going to briefly cover about how AI and ML is changing the scene for the science of gaming, which is what we promote at our organization. So before we move forward, a brief introduction to Games 24/7. It is the largest multi-game platform at a very high industry-leading scale and gamer engagement. We have products across multiple different types of games. Card games, which is represented by Rummy Circle, which is the #1 Rummy game in India. My 11 Circle is representative of our offering in the fantasy sports, and it's established as the #2 in the country. And we have our U Games division, which is the casual gaming studio, driven by a very, very mature content production pipeline and platform. And we recently launched Play Circle as semi-casual skill games platform offering multiple different types of games. We have as it is evident, we have an expanding portfolio of products driven by the new innovation, as well as the established brands expanding via new innovations and features as part of it, right? Together, we host around 100 million plus players in our platforms. Rummy Circle itself hosts around 4 billion rounds of plays annually in the platform, and overall, an average time spent by a daily user is around 1 hour per day. So this expanding portfolio, which is what we have established over the years, is also having a large addressable market and a very strong outlook in the coming few years, with around 45% CAGR growth rate to reach over $10 billion in terms of market size and the revenue opportunity. And it is evident, right, and without getting into too much details on the data, that for all the sectors or all the types of games that we offer, right, the growth rate is pretty similar, if not more, across sectors. One of the key things that we believe in that will drive this growth, of course, among many other things, but not more important than how AI, ML, and data science will drive the innovations and features in the space in the coming years. And in that regard, we found ourselves uniquely positioned because we have been pioneering the AI and ML efforts in online gaming space, especially in skill gaming, for the past 3-4 years. And we continue to invest heavily in our AI and data science platform, which underpins all of our products. We have established a very mature AI ML pipeline to perform a whole gamut of modeling and analysis across 3 major verticals of game, content, and process AI, where game AI focuses on inside game analysis and modeling. Content AI is more about hyper-personalization, which essentially means what kind of content users are going to see in the platform, and process AI is all about automation of various different processes across the organization and the processes that touch our users, right? We have deployed AI and ML modules in all of these verticals, which has enabled us to be very outcome-oriented platform, which essentially means that every touch point of our users in our platform or as part of any process, more often than not, will touch some AI and ML module, which has been developed using state-of-art solutioning to solve very, very unique business and technical problems that enables a lot of benefits and differentiation, which is all powered by a huge volume and velocity of data, as well as diversity of data We generate around 7 terabytes of data per day across all our platforms that you have seen. And we have been investing very heavily in AI research and end-to-end informatics and intelligence, which kind of comes together in this 360-degree functional view of AI ML, where we have data in the left-hand side of this diagram, which kind of cuts across inside the game-related data, game choice, game outcome, to other platform data like clickstream, transactions, demography of users. And then based on all of this data, how we can come up with a gamer insight layer across their core gameplay inside the game, their skill rating, their mistakes, so on and so forth, and their platform interaction, how that all leads to various different kind of engagement behavior and other kind of behavior on the platform. And then once we have that gamer insight done, we can do all sorts of experimentation and recommendation, often using very, very cutting edge solutioning, such as using reinforcement learning and all of that. And then that leads to finally hyper personalization on various different fronts, from product journey optimization to process optimization, as well as campaign. Now, one of our motto is to do all this hyper personalization with a high degree of responsibility, which is where we believe in very, very strongly. And we drive all of this kind of work using some major research that gets into all of this direction, like explainable AI, generative model to from an art creativity point of view, recommender systems, cognitive neuroscience to understand our users better from the telemetric data, stochastic optimization, reinforcement learning, as I already mentioned, for game modeling as well as for hyper-personalization purposes, sequential modeling to understand the evolution of our gamers on our platform better, computer vision to represent the game states as images, as well as for various art and creativity related game production activity, and deep learning in general cuts across all the different problem spaces that we work on. So with that, I'll conclude this presentation. Thank you everybody for hearing me out. We are always in the lookout for great talent, and please feel free to contact me or Vikrant, who is our HR leader, if you are interested to know more. Thank you.
So thanks a lot, everyone. I think Trideep is also here. So if there's any question for Trideep, please just post or raise your hand maybe. And thank you, Mayank, and thank you, Vivek. I actually forgot to ask. We did have another question. Is there like the resources in terms of code data? Is anything available? Can the participants get get in touch with you perhaps to get that? Is there any way of getting that?
So there are two things that I want to mention. So first is all the resources that we have worked on recently. They are all available. They are available on my website, as well as you can go to Lingo ITGN website. They are there. And there is one NLG share task we are hosting. Maybe in a couple of days, the website will go live. So if you want to participate in that kind of thing, maybe NLG evaluation, if that attracts you, maybe you can do that. And it will be a good learning experience. We can promise that, because the task is quite good.
That sounds fantastic. So I think Trideep, if you will switch on your video, we'll just click a snapshot here. Yeah. So I think it's done. Thank you so much, and thanks a lot, Kala, for inviting me to chair the session. It was such a fantastic session. So many people, so many questions. Thanks, Mayank. Thanks, Vivek. Hope to see you physical next year, hopefully. Yeah. So thank you. So I think
thank you so much, everyone.
Thanks, everyone.
we
Thank you all. Bye.
can end the session. Yeah. Thanks. Bye.